Hi everyone, welcome back to the SKKU 2025 Quantum Challenge problem. It's me again. My name is Yupin Lin and I'm a senior scientist in quantum chemistry at IMQ. I'm the designer of the challenge problem about the measuring Berry phase in quantum computing. And today I'd like to explain to you the solutions to the questions in this challenge problem. So as you can see, we have three major parts of the challenge problem. The first part how is about the theory of the Berry phase. The second part is how we measure it with the quantum circuits, and the third part is about applying the first and second parts to see how we can classify the topological phases and detect them in a non-interacting or interacting fermion model. Yeah, so let us begin part by part. And also, I want to mention that, I have submitted a Jupyter notebook, as you can see here, including the detailed solution, and I hope you can find it, from the official. Yeah. Okay. And also because there are many problems, I'll tie to the center spirit of the problems, and you can find the details in the Jupyter notebook. Yeah. So the first part is about the theory of Berry phase. So we want to consider a time evolution of a quantum state under a time-dependent Hamiltonian. Particularly, we want the time-dependent Hamiltonian to change slow enough so that we have the adiabatic theorem. That is, if you begin with an eigenstate of the initial Hamiltonian, the quantum state will remain an eigenstate of the time-evolving Hamiltonian at the same level. So we can write the quantum state as a multiplication of a complex phase with the eigenstate of the time-dependent Hamiltonian. So question one is I wanted you to compute the complex phase, and it will be composed of a dynamical part and a Berry phase. And the Berry phase is the central part of our study. Yeah, so the solution is quite straightforward. We just take the time-dependent Schrödinger equation and take the inner product with the time-dependent quantum state, and we can plug in the adiabatic form of the quantum state to both sides of the equation. And for the right-hand side, it is straightforward that it is the time-dependent eigenenergy. And for the left-hand side, you'll find that it will include the time derivative of the complex phase and the time derivative of the time evolving eigenstate. And the time evolving eigenstate will through some computation, give us the result of the Berry phase. That is, it will be an integral in time of the derivative of the quantum state, and you can transform it into a derivative in the parameter space. So because you can transform it into a derivative into an integral of the derivative in the parameter space, the Berry phase is essentially dependent of the path the time dependent Hamiltonian go through in the parameter space. So we can see in questions 1.2 and 1.3, we are essentially looking at how the path can affect the Berry phase. Yeah, so here we take a simple example, that is, we take the Bloch sphere Hamiltonian, which is a 2 by 2 Hamiltonian, and we can define the Hamiltonian in terms of the Pauli matrices X, Y, and Z, and a three-component real vector H. And H will be the parameter that we use, and the parameter space is just the three-dimensional space. Yeah, so question 1.2 is straightforward. It is just computing the eigenstates and their energies. And yeah, so you can find that the eigenstates there is a two-level system, and it's plus minus the magnitude of the block vector, that is the three-dimensional vector H. Yeah, and here we focus on the case where the block vector is a unit vector. That is, it will traverse on a unit block sphere around the origin of the parameter space. And in question 1.3, I wanted you to compute the Berry phase of the four different paths on the block sphere. So yeah, I wanted you to consider to keep track of the overlap of the time-dependent phase with the initial state, particularly plot out the amplitude and also the complex phase, either the total complex phase or the one where the dynamical phase related to the energy is excluded. Yeah, and because we are for the case we consider the ground state energy is -1, if we take the time to be a multiple of 2 pi, we can at the end of the trajectory, the dynamical phase will just be equivalent to 0 modular 2 pi. So the final total phase will just be the Berry phase that we want to look at. So I will skip the code part, which you can look into the details from a Jupyter notebook, and I will just show you the result. So if we are looking at the constant Hamiltonian where the block vectors stay at the same point, then we can see that the overlap will remain 1. The magnitude will remain 1. Meanwhile, the complex phase will oscillate, which is the dynamical phase oscillation related to the energy, but the Berry phase will remain 0. But if we start to have non-trivial trajectory under time evolution, we will see that the overlap will have an amplitude change over the time evolution, and there will be a dynamical phase oscillation as well, but there will be some further contribution from the Berry phase. And at the end, you will find that the total Berry phase will go to 1. And yeah, so this is different from the 0 we saw from the last example. And if we now go through a trajectory like this, going from positive x to positive y to positive z, then back to positive x, we will see that the Berry phase will accumulate to -1/4. And lastly, for this kind of trajectory, we will see that the Berry phase will go to -0.5. So an important question is, how is the Berry phase related to the trajectory? In fact, you can think of it as being related to the area of that the trajectory surround on the unit block sphere. And the reason is that if you look at the formula of the Berry phase, it is a closed integral of the Berry connection. And if we use the Stokes theorem, we can transform it into a surface integral of a B vector, where the B vector is the curl of the Berry connection, which is the Berry curvature. And an important point is that for the block sphere Hamiltonian, we can think of the Berry curvature as the magnetic field originating from a monopole at the origin. And for a unit block sphere, the magnitude of the Berry curvature are the same along all directions. So you will see that. So the Berry phase accumulated will just be proportional to the area that the trajectory surrounds. For example, for the constant Hamiltonian, you have 0 area, so it is essentially 0. And for the closed trajectory like this, it is half of the block sphere, which is just and you will see 1. And if it is like this trajectory, then it is 1/8 of the total area, so it will be 1/4 in the Berry phase. So, and finally, for this, it is 1/4 of the total area, so it will be -0.5. Yeah. So you can learn more about this in one of my previous papers. So we have learned how the Berry phase originates from the adiabatic time evolution. The next step is to see how to measure it with the quantum computer. So we know that the Berry phase is the total phase of a quantum state. So you cannot just simulate the quantum state with all of your qubits and try to measure the phase. But we cannot measure the total phase, but we can measure the relative phase between different component states of a superposed quantum state. And to use it, we can use this property to measure the Berry phase this is the central part we do in the second part of the challenge problem. So before we go into the berry phase in question 2.1, we want to understand how we measure the relative phase of the component state through the interference. So we consider the single qubit state with 0 and 1, and we consider relative phase between them. So we want to use the interference to measure the relative phase. And the way to do this is to apply a Hadamard gate to the quantum state so that you mix the 0 and 1 states, and the complex phase is transformed into the component of the new 0 and 1 state. So that if we measure the quantum state from the probability of measuring 0 and 1, we can get the information about the relative phase. Yeah, and this is the way how we measure the relative phase with the quantum circuit. So with this knowledge, we can now see, and the quantum circuit look like this. We just apply a Hadamard gate to the state and do the measurement. And with this knowledge, we can now think about how to use it to measure the Berry phase of a quantum state. So the question 2.2 is to consider a constant Hamiltonian before we go into the more complicated time-dependent Hamiltonian. So the way we do this is that uh, we use a register of qubits to simulate the quantum state. And here to simulate a quantum state. Meanwhile, we add one additional qubit to the system, and we want to encode the complex phase from the time evolution of the quantum state to the attached qubit, which we call the ancilla qubit. Yeah, so the way we do this is to consider, as we mentioned, attach a single qubit to the quantum state we want to simulate. And first, we will apply a Hadamard gate to get both 0 and 1 states. Then we will use a controlled unitary, that is, we apply the unitary time evolution to the quantum state only if the ancilla qubit is in the 1 state. And so the result state will only have the dynamical phase in when the ancilla qubit is the 1 state. Then we will, as in the previous question, apply the Hadamard gate to the ancilla qubit. Then we can transform we can transfer the dynamical phase to the 0 and 1 state amplitudes of the ancilla qubit. Then we can measure the ancilla qubit to get the information about the dynamical phase. So the quantum circuit look like this. We first apply a Hadamard gate, then we apply a control unitary to evolve the target state. Then we apply a Hadamard gate to interfere the ancilla qubit and do the measurement. Yeah, so we have learned how to measure the Berry phase with the addition of an ancilla qubit. Next, we want to apply to the block sphere Hamiltonian we studied in part 1. So here we will use the state vector sampler in Qiski to do the measurement. And the quantum circuit is pretty straightforward. As shown previously, we use the Hadamard gate to prepare the ancilla qubit, and we use some single qubit gates to prepare the initial ground state of the initial Hamiltonian. Then we apply the time evolution in a discrete way because we're doing the numerical time evolution. We need to discretize the time step and apply the control unitary one by one. And at the end, we interfere the ancilla qubit with the Hadamard gate, and we do the measurement. So so let me show you the results. So indeed, for the constant Hamiltonian, we see that the final result, the final state of the ancilla qubit is just a 0 state, and the resulting Berry phase is 0. Meanwhile, if we go around the block sphere in the parameter space, we will see that the final state of the ancilla qubit will just be 1. So we will get the corresponding Berry phase 1 times pi actually, sorry. And if we go through this kind of trajectory, which is 1/8 of the block sphere, we'll find that there is a ratio between the probabilities of 0 and 1 such that the Berry phase over pi is about 1/4. And finally, for this 1/4 surface area of the block sphere trajectory, we will see that the 0 and 1 state roughly have the same probabilities. So we will get the Berry phase roughly 1/2. Yeah. So this is how we can measure the Berry phase with the quantum circuit, and we have demonstrated it with the example of the Bloch sphere Hamiltonian. So we have learned the theory of the Berry phase, and we have learned how to measure it with quantum circuit. And in the third part, we want to apply our knowledge to a practical model, which we call a Schiffer-Heeger model. It is a fermionic model with topological phase transition, and we can see how Berry phase help us distinguish different topological phases. So as you have already learned, the Schiffer-Heeger model, that is the SSH model, is a non-interacting fermionic model. Actually, for the spinless fermions. So we will have alternate bond strengths, the red bonds and the blue bonds. And if the red bond is stronger than the blue bond, then the system at half filling will be a trivial insulator. But if the red bond is weaker than the blue bond, then at half filling it will be topologically non-trivial. Particularly, it will have some edge states within the band gap. So we can see this from the spectrum. So the positive delta J case is the case where the red bond is stronger than the blue bond. And you can see that it is a trivial insulator where within the gap there is no state. But for the negative delta J case, you can see that there are a pair of states here. And if we look at the distribution of the amplitude of these two states, you'll find that the density will be concentrated at the two edges. So we have a pair of in-gap edge states. So yeah. And an important property is that the existence of the in-gap edge states is related to the non-zero polarization, which is zero or non-zero for the cases without or with the in-gap edge states. And the important message for us is that the polarization is related to the Z phase, which is essentially the Berry phase within the momentum space. So our mission is to find a way to compute the Berry phase in the momentum space and use it to detect the topological phase transition, that is, whether the polarization is zero or non-zero. Yeah. So question 3.1 is to perform the Fourier transform into the momentum space. And this question, at the end of the calculation, we will be able to find a Bloch sphere Hamiltonian, and we will have a Bloch vector like this. So the Fourier transform is straightforward, and yeah, you can look at the details within the Jupyter notebook. And one point I do want to mention is that under a Fourier transform, the non-trivial part comes from the Fourier transform of the nearest neighbor terms between different unit cells. And here we have unit cell because we have strong and weak bonds, and the periodicity of that is 2, and so we have the two-side unit cells. Yeah. So within the momentum space, because we have two-side unit cells, we will have a 2x2 Bloch Hamiltonian, which is the function of the momentum. And yeah, and if we diagonalize the Bloch Hamiltonian, we can find the band structure in the momentum space, and you can see that the band structure like this. So if delta J is negative, then the trajectory of the Bloch vector within the momentum space will enclose the origin of the two-dimensional momentum space. And as we see previously, in three-dimensional parameter space, the origin can be thought of as the monopole of the Berry curvature. And in a two-dimensional case, the origin is actually a vortex of the Berry phase. So if the trajectory of the Bloch vector surrounds it, we will have a non-trivial topological phase. But as the delta J changes, the trajectory will gradually tune away from the origin. And and for the positive delta J case, the trajectory will not enclose the origin, so we will have a topologically trivial phase. And the case where delta J is equal to 0 is where the trajectory touches the origin, and you will see a band gap closing, which indicates a topological phase transition. Yeah. So this is the question 1. And after having the block Hamiltonian, and we can now use the techniques we learned from part 1 and part 2 to measure the Berry phase. And here, one important difference is that our in part 1 and part 2, our our energies, which is the eigenvalue of the Hamiltonian, is constant throughout the time evolution. But in the block Hamiltonian, the energy is not a constant. But we can use a trick called a half-time reversal. Um, that is, we can evolve the time forwardly in the first part of the momentum space, that is the Brillouin zone. And in the second part of the momentum space, we can evolve the time in the backward way, so that the dynamical phase in the two parts will cancel with each other, but the Berry phase does not depend on how you evolve the time, so it will accumulate normally. So at the end, the total quantum phase, the total complex phase will not have dynamical phase and only have the Berry phase. And this is a trick called the half-time reversal evolution. Yeah. So as in part 1 and part 2, we will compute the overlap of the time evolution and also the quantum phase. So 3.2 is to use this to measure the Berry phase at different value of delta J. So so the result is like this. For negative delta J and positive delta J, we can see that the overlap magnitude is essentially 1. And close to the phase transition, there is a significant drop. It is because the discrete time step we choose is not small enough to so that it is larger than the energy gap close to the phase transition, and the adiabatic theorem will fail in this kind of case. But the important point is that away from the phase transition, we still have a amplitude close to 1, so the adiabatic theorem is still very good. And we can see that the Berry phase is 1 in the negative delta J regime, and sorry, the and 0 in the positive delta J regime. So yeah, so we have a non-zero Berry phase in the topological phase, and the zero Berry phase in the topological trivial phase. So this is consistent as with what we said previously. Meanwhile, in the quantum circuit measurement, we can do the same thing as in part 2, and we can see that the result is consistent with what we did with the overlap computation. We see a non-zero close to 1 Berry phase in the topological phase, and close to 0 Berry phase in the trivial phase. So yeah, so for a non-interacting SSH model, we indeed have the topological phase transition. So the Berry phase does not only classify the topological phase in the non-interacting phase. In the non-interacting regime, it also applies when the fermions are interacting, that is, they may be attractive or repulsive to each other. And to study this kind of topological phases in the interacting fermion model, here we introduce a nearest neighbor repulsion to the SSH model. And because of this, repulsion, we cannot study it in the momentum space in a simple way. So here we will, and yeah, so we will need to stay in the lattice model. But we know that the fermionic lattice model is usually very hard to solve directly because there are some fermionic exchange. We may involve some complicated minus signs. So here we will use a powerful Jordan-Wigner transformation to transform the fermions into the qubits. And yeah, so the fermionic creation operator is related to the level down operator in the qubit model, and the annihilation operator of the fermion is related to the level up operator in the qubit model. So yeah, so question 3.3 is to ask is that I want you to confirm that the properties of the Fermionic operators are preserved under the Jordan-Wigner transformation. That is, the density operator is characterized by the Z qubit operator, that is a Z polymatrix, and the Fermionic exchange is still preserved under a Jordan-Wigner transformation. And so you can look at the details from the Jupyter notebook. And the essential point is that if our fermionic operators are at the same site, then we will have the anti-commutators between x and y on the same sites. So we will have a non-trivial result. But if we have the fermionic operators at different sites, then we will have the anti-commutators between x, y, and z, and we know that it is zero. So for the Fermionic operators between different sites, the anti-commutation relation will always be zero. So this is an important point. Yeah. So now we want to, we can obtain the qubit Hamiltonian from the fermionic Hamiltonian. So we want to transform our fermionic model, SSH model, to a qubit model. So here we will consider periodic boundary condition model, where we connect the first and the last sides of the SSH model. And question 3.4 is that I want you to derive the qubit Hamiltonian of this periodic model. And so the important result is that the nearest neighbor hopping will be transformed into the XS and nearest neighbor XS and YY couplings, and the nearest neighbor repulsion will be transformed into the nearest neighbor ZZ coupling. And meanwhile, we also, because we are using the periodic boundary condition, we will have a hopping between the first and the last sites, and we will still have the XX and YY couplings, but we will have we'll have a string of the poly Z operators between the two sites. Yeah, so this occurs for the XS and YY couplings. And so in a non-interacting case, we use the momentum as the adiabatic parameter to measure the Berry phase. But in a lattice model, we don't have this kind of momentum, so we need to find a way. And if you still remember, for the Fourier transform of the non-interacting model, the nearest neighbor hopping will generate a complex phase exponential negative ik. So here we are motivated by this complex phase, so we can introduce a complex phase e to negative I5 to mimic the momentum in the Fourier transform. And particularly, we will add this complex phase to the periodic boundary condition bound, that is the connection between the first and the last bound. We will add a complex phase to this single bound and see if we can measure a change in the local topology. And this kind of change in the boundary condition is sometimes called the twisted boundary condition. And we will vary the complex phase from 0 to 2 pi and see if we can get the non-trivial Berry phase. And because we have introduced this kind of phase twisting, in question 3.5, I wanted you to rederive the qubit model of the interacting SSH model. So the major change is that now for the coupling between the first and last bonds, we not only have the XS and YY couplings, we will also have an XY and YX couplings, and this is a major change of the for the Jordan-Wigner transformation. And the remaining part of the qubit model is the same as the previous one. So we have got the qubit Hamiltonian we want to study, and we can now use it to measure the Berry phase. So in question 3.6, I want you to use the qubit Hamiltonian to confirm the topological phase transition in the non-interacting case, but now with the lattice model. So so it is just and one important point here is that because we're looking at half fitting, but our full qubit Hamiltonian contains the quantum space of all of the fittings with different particle numbers. So we need to write down a projection projector to project out the Hamiltonian to the half-fitting subspace so that we can get the ground state within this subspace. And the way to do this is to remember that the number operator is related to the z operator. So the computational basis are good eigenstates of the particle number. So we can just compute the particle number of each of the computational basis states and find out the projector that projects only onto the ones that correspond to the half-fitting subspace. So after this, we can do the time evolution as in the previous results. Only let our target so for the overlap computation, we can see that it is consistent. We have the overlap with a significant drop close to the topological phase transition, and we have the Berry phase, -1 Berry phase in the topological phase, and the 0 Berry phase in the trivial phase. And meanwhile, our quantum circuit will not include 8 qubits because we're considering an 8-side lattice. And the result of the Berry phase measurement is also consistent. That is, we have Berry phase 1 times pi in the topological phase and the 0 in the trivial phase. And in question 3.7, I want you to study the case where we now have non-zero interaction. And here we will start from a non-interacting topological phase in the negative J region. And we turn on the interaction and see if we can see a topological phase transition. So indeed, we can see a topological phase transition. Here we can see that in the small interaction regime, we have the non-trivial phase. And in the strong interaction regime, we have a trivial phase where the Berry phase goes to 0. And we can see that there is a significant drop of the overlap across the phase transition. And the measurement from the quantum circuit is consistent. We have close to one Berry phase in the small interaction regime and a very small Berry phase in the strong interaction regime. And the reason why the Berry phase measure in the quantum circuit doesn't go to 0 is probably because we have a very strong drop in the amplitude, so that there will be some mixing. The 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 quantum state may not evolve back to itself after a time evolution, and the Berry phase will have some contribution from the state mixing. So we have got two different trivial phases in the non-interacting regime with positive delta J, and in the negative delta J region with a very strong interaction. So we may want to know if the two trivial phases are the same. So question 3.8 is pretty simple. I just want you to find out the phase diagram at half fitting by tuning delta J and V and see if the two states are the same. And the way we do this is to look at the energy gap between the ground state and the first excited state. So we will project the Hamiltonian to the half-fitting subspace and compute the energy gap. And the result is like this. We can see that in the non-interacting regime, we do have a gap closing. That is, the gap is close at 0, at delta G equals 0. And if we have an open boundary condition, this one is topological and this one is trivial. Meanwhile, if we turn on the interaction, we can see that it will go into the large regime where the energy gap essentially closes. So we can see that the phase is different from the positive delta J non-interacting state. So we may want to ask what state this is. So in fact, in the strongly repulsive regime, the ground state is degenerate. It is the charge density wave degenerate state where there are two different ground states. The first one is with all of the charge densities accumulating on the first sublattice, and the second one will be all of the densities accumulating on the second sublattice. That is, you will have degenerate ground states of 1010 and 0101. And that is the reason we have a very close energy gap in the strongly repulsive CEW regime. So this is a complete description of the repulsive SSH model. So this is the end of the challenge problem solution. And I know it is a bit long challenge problem, but I hope that through this challenge problem, you have learned the essential concept of the Berry phase and learned how to measure it. And you have learned one of the important applications of the Berry phase within the condensed matter physics. And I hope that this will help you figure out maybe some interesting research directions in the future. And yeah, that's the end of my explanation. And thank you for your listening.